Okay, so our last section of this lesson talks about covalent bonding in ionic species. So we have these special type of ions that we call polyatomic ions, and they consist of a combination of two or more atoms. Specifically, they are covalent compounds, so they have bonds. That's very important. They have bonds. They are between nonmetals. So a polyatomic ion is nonmetals. But they are ions. That's a key word, that they're ions, so they're nonmetal ions that participate in ionic bonding. Because those are ions, they have a charge to them, meaning they would be attracted to metals, which is a definition of ionic bonding. So, the formulas are determined following the same rules for ionic compounds containing only monoatomic ions. So we follow our ionic compound naming rules and formula rules that we talked about in our previous lesson. So the ions must combine in a ratio that gives a neutral formula overall. So here's one of our polyatomic ions. It's called phosphate. You see that phosphate is made up of phosphorus and oxygen, but it has a special name to show that it is an ion. It's not phosphorus tetraoxide. Okay, it doesn't have a name like our typical covalent compounds. It's a polyatomic ion, so it has a special name. Okay, and it has a charge of 3-. Because it has a charge, an overall charge, it is attracted to a metal. So here we have calcium 2+. Okay, so we use our typical crisscross method. So our 3 goes down to the calcium, and our 2 comes down to the phosphate. Because to balance out the charges, I need 3 calciums with 2+ charges and 2 phosphates with 3- charges to create a compound that has an overall neutral charge. The thing here is when we have a polyatomic ion, we put it in parentheses and then put our subscript on the outside of those parentheses to show that this applies to the whole ion itself. Polyatomic ions stay together. We would not write this as Ca3P2O8. I wouldn't bring that 2 in. We would not write that way. Okay, we keep our polyatomic ions together. So we treat how we write their formulas and name them in the same way that we do ionic compounds. So what we do is we would name these. So this formula, let me erase some of this so we can see it. Okay, this formula is calcium. We name the first one calcium. And then for polyatomic ions, we just keep the name the same. So this is phosphate. We don't worry about the ID ending. We don't put in an ion or anything like that. We just say calcium phosphate. And again, just like ionic compounds, if we know the name, we can then know the charges because our polyatomic ions have specific charges. So there is a long list of polyatomic ions available on eLearning in our list of elements to know from this chapter. We've already looked at it in our previous lessons to learn about our ions and the elements that are handy to know right offhand, so their symbols and their names. There's also a list of polyatomic ions in there as well. Those you should also start to know, start to learn, create some flashcards so you can start memorizing them. You need to know their name, their formula, and their charge. Okay, those are all very important. So what I want you to do is pull out that elements to know page, whether you have it up on your screen or you've printed it out. You should have it somewhere on you for what we're going to do for the rest of this lesson. So please get that out. And what I want to do is go through a few of these polyatomic ions together so that we can start to see some of the trends in their names and their formulas. Okay, so looking at your elements to know chart, let's write the formulas for the nitrate and nitrite ions. So they have slightly different endings, nitrate and nitrite. Well, nitrate is NO3 with a -1 charge, and nitrite is NO2 with a -1 charge. So when we went from 8 to ite, we lost an oxygen. So an ite has one less oxygen than an 8. Ite has one less oxygen than an 8. Okay. So that's what happens to the oxygens in our polyatomic ions. Let's look at a few more. Let's write the formulas for the sulfate and the sulfite ions. So again, we have that 8 and that ite. Let's look it up on our list. Sulfate is SO4, 2-, and sulfite is SO3, 2-. So again, the ite has one less oxygen than the 8. Now the 8 and the ite don't tell us the exact number of oxygens, it just tells us relative to that specific 8. So nitrate had NO3 and nitrite had NO2. So it's not like the 8s all have 4 oxygens or 3 oxygens. It just is whatever the 8 is, the ite will always have -1 oxygen. The charges are the same and everything, okay? Next up, we have the chlorate kind of sequence. So there's 4 of those. There's perchlorate, chlorate, chlorite, and hypochlorite. So look those ones up on your list of elements to know. So perchlorate, I'm just going to write it there, perchlorate is ClO4-. Just chlorate, so I'm going to put ATE here, is ClO3-. Chlorite is going to have one less oxygen than that, so Cl2-. And hypochlorite is going to be ClO-. So with each one, we are losing an oxygen, but everything else is staying the same, the charge, as well as the number of chlorines. We're just changing either the ending or the prefix of those. Okay, so when we're naming, when we're writing the formula, when we're writing the chemical formulas with our polyatomic ions, what we want to do first is write our positive ion first, so that's going to be our cation. We then want to write our polyatomic ion next, our anion. Most of our polyatomic ions are anions except for NH4+. So just keep that in mind. Most of our polyatomics will come second, except for NH4, which is ammonium. Okay. Then what you're going to do is our crisscross charges to create our electrically neutral compound. And if more than one polyatomic ion is needed, we're going to put it inside parentheses and place the subscript outside of the parentheses, like we saw in our previous example. And what we're not going to do is change the subscripts on our polyatomic ions. We are not changing those. Those stay the same. We keep our polyatomics together. You can see them as one unit. So, like NO3, it looks like this. It has these bonds on it, and there's an overall charge of -1. It stays bonded together. It's not like we're breaking any bonds. When I say that there's 3 of them, I just mean that I have 3 of these structures all together. Okay, so there's multiples of them, but they are each their own unit. So that's why we put them in the parentheses. Okay, so let's do the example of magnesium and nitrate. So I just had nitrate on there. That's NO3-. Okay, so we have magnesium. We have to follow our regular ionic compound rules for writing the formula, so we need to know the charge of the magnesium. Well, magnesium is a main group element. It is in group 2, so it has a 2 plus charge. I then have nitrate, NO3, which has a 1 minus charge. If I put those together in a 1-to-1 ratio, I have an overall charge of +1, which is not neutral. So in order for this to be neutral and cancel out, I need another nitrate in there to create a 0 charge overall. I have to balance out that 2 plus charge of the magnesium with 2 nitrates. So my formula would be MgNO3 2. So I'm putting the 2 to denote that I need 2 nitrates on the outside of my parentheses. We don't want to do this, MgNO3 2, because then that would look like there's 32 oxygens and 1 nitrogen, which is not correct, so we don't want to do that. Bad. And we also don't want to do MgN2O6, because then that's not a polyatomic ion anymore. So we also don't want to do that. We just want to keep our polyatomic together as it's one unit, and we want to put our subscript outside of those parentheses. Okay, think of it like a little package. So let's do some more practicing. So we want to take these names and we want to write the formula of the ionic compound that is formed. Okay, so here we have sodium and bicarbonate. So we know sodium, we know its charge has a +1, right? It's in group 1, so it's going to have a +1 charge as an ion. Bicarbonate is on our list. It is HCO3 minus. So they have equal but opposite charges, meaning that this chemical formula, this ionic compound, is NaHCO3. It's neutral, there's no charge. If you wanted to keep the polyatomic together, if it's easier to see that way, you're welcome to put it in parentheses. Okay, that's totally fine. Next up, we have potassium and nitrate. Well, potassium we worked with before. That has a 1 plus charge. Nitrate we've worked with in our past few examples. That's NO3 minus. So those have equal but opposite charges, so they combine in a 1-to-1 ratio. So we get KNO3. So we could put that in parentheses as well if it's easier to see that polyatomic ion together. Next up, we have 2 polyatomic ions coming together. So ammonium is our 1 cation, our polyatomic cation. So that has a formula of NH4+. Then we have sulfate, which is one of the ones that we looked at before. So sulfate is SO4 2-. So in order to balance out these charges, I need 2 of these NH4s to balance out my charge of the SO4. So I'm going to put my NH4 in parentheses with a 2 outside of it because I need 2 of them. And then I'm going to put my sulfate SO4 outside of that. We don't show any charges because it is now neutral. Okay. Now what I want you to do is try these last 3 on your own. I will make a note that bisulfate is not on our list, but you can deduce what its formula is because we have bicarbonate. Carbonate by itself is CO3-. Bicarbonate is HCO3-, so we just add a hydrogen, so that bi means add 1 hydrogen. So bisulfate would be HSO4 2-. Okay, so now use your list and determine what these compounds would be, what their formulas would be, based off of their polyatomic ions. I think we looked at something similar to magnesium phosphate before. I think we did calcium phosphate instead, but magnesium has a 2+ charge, and phosphate is PO4 3-. So we could use our crisscross method here, make it a little bit easier, and we would get Mg3 PO4 2. So that would be our formula. We need 2 of these PO4 3- to balance out the 3 magnesium 2+. Okay, so next up we have calcium and bisulfate. Well, calcium, we've looked at before, has a 2+ charge because it's in group 2. And we said that bisulfate is HSO4 2-. So those would come together in a 1-to-1 ratio to be CaHSO4. And if you wanted to put a parenthesis around that, you could, just to show the difference. Our last example is barium hydroxide. So barium is also in group 2, a lot of group 2 compounds over here. Group 2, so barium has a 2+ charge. Hydroxide is OH-, so it has a -1 charge. So I need 2 of those hydroxides to balance out my 2+ of my barium. So we get BaOH2, making sure to put the parentheses around the OH and the 2 on the outside. Okay, we don't want to show BaOH2 because that would look like there's 2 hydrogens and 1 oxygen, which is not correct. Okay, so that's not how that works. Okay. I think our next thing has this. Oh, so now we're going to talk about how we can name our compounds with polyatomic ions. So when it comes to naming these compounds, we're going to follow the same rules as our ionic compounds. There's just going to be one small change, and we've talked about that a little bit when we first started talking about polyatomic ions. So you'll name the cation. You'll still omit the word ion and use a Roman numeral if the cation can have more than 1 charge. So that's going to be our transition metals again. Okay, so our transition metals are going to have our varying charges, so those need our Roman numerals. When we name our polyatomic ion, we do nothing. We don't change the ending, we don't put an IDE or anything like that, because the polyatomic ions have specific endings based on their specific formulas, which is what we looked at when we looked at perchlorate, hypochlorite, chlorate, chlorite, sulfate, sulfite. Okay, they all have specific endings that we're not going to change. So we're just going to put the name of the polyatomic ion, omitting the word ion. So let's look at this one. Here we have potassium is K. Okay, so our first one is name the cation, potassium. Since potassium is a main group element, it's not a transition metal, we don't need a Roman numeral. Okay, so that's step 1 done. Then we just name the polyatomic ion. So SO4 is sulfate. So this would be potassium sulfate. Okay, and just like with our ionic compounds, we don't need to put any prefixes or anything like that, because if we know the name, we then know the charge from either the periodic table or now from our chart of polyatomic ions. So we know all of that information. So no use of prefixes here, because this is ionic bonding. So let's practice. So each of these compounds contains a polyatomic ion. Determine the name using our rules of naming ionic compounds from lesson 1. So we're ignoring all of our prefixes because these are not covalent compounds. These are ionic compounds. So we do not use prefixes. Okay. So, our first one, we have Na2CO3. Well, we know Na, that's sodium. We then have to figure out what CO3 is. If we look on our list, it's carbonate. Sodium is a main group element, so we don't need any Roman numerals on there. So our name of Na2CO3 is sodium carbonate. Next up we have calcium hydroxide. Next up we have CaOH2. Ca we know is calcium, so we're going to name calcium. It's a main group element, so it does not need a Roman numeral. OH, we've used that before, that's hydroxide. So just like we did in lesson 1, we name the first and then we name the second. The only thing is our polyatomics just have special names that we don't have to change. Okay, next up we have MgNO3 2. Mg is magnesium. Okay, that's a main group element. That also does not require us to use a Roman numeral. NO3 is nitrate, so we just put nitrate in there. Our last 3 examples I would like for you to try on your own, so pause the video and try naming these last 3 compounds. Remembering here, this is going to be bisulfite. There's another one of our examples where we added a hydrogen, so adding hydrogen means that there's a bi in front of it. Okay, so try naming these last 3 compounds. In our next example in D, we have manganese. Mn is manganese, which is one of our transition metals. So we have to use a Roman numeral. So we have to determine its charge. Well, let's think of what our polyatomic is here. This one is acetate. Acetate has a +1 charge, so we have CH3CO2 with a -1. We know from the formula that there's 2 of them, so we get CH3CO2-, there's 2 of those. So we have an overall contribution of 2-. So if there's only 1 manganese, because our formula says there's only 1, in order to have a neutral charge, this has to be 2+. So our name would be manganese 2 acetate. Our next example starts with iron, which is another one of our transition metals, and it can have variable charge as well. So we have to figure out what its charge is. So bisulfite has a charge of +1, or sorry, -1. So bisulfite is HSO3 with a minus, HSO3 with another minus. There's 3 of them. Okay, so that has an overall contribution of 3-. So our iron has to have a charge of 3+ to balance it out, and there's only 1 of them. So our name would be iron 3 to show that it has a 3+ charge bisulfite. We could also determine this from the reverse crisscross method. So we could take the 3 and say that it came from the iron. And our last example here does not require a Roman numeral because it's magnesium. So you have magnesium. Our last polyatomic ion there is phosphate. So this would be magnesium phosphate as our last one. Okay. So before we finish up this lesson, let's just bring everything together from our last few lessons, and let's fill in this table with our cations and our anions using our polyatomic ions, as well as just our regular rules for ionic compounds. So our first example has magnesium bicarbonate. Bicarbonate, that's one of our polyatomic ions. It's HCO3 minus. Okay, that's our, if you look on your list, that's where it is. Okay, magnesium is Mg2+, so those are our cation and our anion. Okay, so our formula would be MgHCO3 2, because I need 2 of these HCO3 minuses to balance out the 2+ charge of the magnesium. Next up, we're given the formula, and we need to find the name and the ions. So Sr, that's strontium, and Cl is chlorine. So we reverse crisscross method this, so the 2 came from the strontium, the 1 came from the chloride. We know both of those because they're main group elements. So strontium will always have a 2+ charge because it's in group 2. Chlorine will always have a 1- charge because it's in group 7 and it only needs 1 electron to get to a full octet. So now we just name this using our ionic compounding rules. So this would be strontium chloride. We name the first, then we name the second using IDE as the end. This has no polyatomic ion in it, so we don't need to worry about eights and ites or anything like that. Okay, this next one, we're given our cation and our anion, and we need to find the formula in the name. So we have iron 3+ and NO2-. So if we crisscross those, we have 1 that goes down to the iron, 3 that goes down to the NO2. So we get Fe, NO2, 3. So we name our first one iron. Iron is a transition metal, so we need to show its charge as a Roman numeral. It has a charge of 3+. That was given in the problem. NO2 is one of our polyatomic ions. That is nitrite. So we leave that name as is. So our name is iron 3 nitrite. Okay, you try these last 2 rows before we finish up this lesson. So from the name manganese 2 chlorate, we already know our cation, manganese, has a charge of a 2+. Chlorate is one of those that we looked at earlier. Chlorate is ClO3-. So the formula becomes MnClO3 2, because I need 2 of the 1- chlorates to balance out the 2+ charge of the manganese. And finally, we have SnBr4. We know bromine has a charge of a -1, and since there's 4 of them in here, that means tin must have a charge of 4+. So its name would be tin 4 bromide. Remember, tin is one of those elements, it's not in the transition elements, but because it's on the other side of the periodic table, it's not in group 1 or 2, it can have a variable charge, so we should always show its charge as a Roman numeral. Okay, so that ends our lesson on covalent compounds and their naming. So up until now, we've talked about ionic compounds, how we name those, covalent compounds and how we name those, and our polyatomic ions and how we name those. So before you move on to our next lesson, where we're now going to start using those compounds and measuring masses and moles and everything of those compounds, make sure that you practice your ALEKS homework and master these skills first before moving forward.